A very good morning to one and all. And today concept is about applications of CFL and the CFGs. And I already said that in the last class we're having some applications of the context-free grammars like an parse trees and as well as the XMLs, all those. And here we're having some of the applications of CFLs and the CFGs. And let's see what are those. And first, the first application of this context-free grammar or context-free language is, and here the compilers use the parsers for syntactic checking. And I think you all know what the compilers are. Compilers are nothing but an mediators in the sense those are acting as a mediator between the input and the output. Whenever you are doing the program execution, I think you all are very familiar with the compilation process, right? So that we can call it as an compilers, and these compilers uses the parsers are nothing but an syntax trees. That means we are representing in hierarchical structures, and for what we are representing the tree structure means for checking out the syntactic whether it is in correct meaning or not, and for checking out that we are using this compilers. So one of the application is that compilers use the parsers for syntactic checkings. And the second application here is it can be expressed, the parsers can be expressed as CFGs. Already I explained with a balanced parenthesis, and here we're having another example with an if then else statement, and we're having some other examples. And because for the construction of the CFGs we're having more and more examples, we can take any type of a language and we can construct the CFGs for those languages. So here how the balanced parentheses are expressed means, see, this is the productions that we're having for the balanced parenthesis. B tends to BB, as I already said that you can choose any variable whether it may be S or E or A or B, whatever it may be. Here we choose an BB, it represents, it is an balanced parenthesis, right? So B tends to BB, or you can also take another rule like in B tends to open parenthesis, B closed parenthesis, or it is any other statement. And what the statement it is. So in this way we can also represent, or we can also express the context free grammars. And here the second thing is if then else. If then else means here we need to take the conditions like if condition then statement else statement, like that. So S tends to SS, or you can take if condition then statement else statement, or if condition then statement, or directly it is a statement. And here you need to define what the condition is and what the statement is, because the condition and statements are the new variables, right? So you need to give an production for these new variables to make it as a live. So these are the ways of expressing the CFGs just by using an parsers. And the third one is here we can also use an C parenthesis matchings. That means these braces C parenthesis matchings also you can use. And we can use the these context free grammars for the Pascal begin and matchings. And also we can use for the ACK is nothing but one of the tool for the compilers, and this is an parser tool. For generating the parsers we are using this tool, and it is also from the Unix utility ACK at another compiler compiles. So these are the applications that we're having here for the context free languages as well as the context free grammars. And coming to the more applications, like we can also use these CFLs or CFGs in markup languages, and this thing I already explained in the last class. XML in the markup languages we're using this context free grammars, as well as in the nested tag matchings. And these are the examples of the nested tag matchings. And if it is an HTML, and this is the way of representing an nested tag matching, and if it is an XML, and this is the way of representing the nested tag matchings. So these are the applications of the both context free languages and as well as the context free grammars. And coming to the tag markup languages, if these are the representations of the tag markup languages. Role, for if you want to represent the tags for the role, you the commands, that means the for the template that you need to follow for representing the role is like this. You need to put the role in Gullmans and then class students, and you need to close the role like this, closing of the role. And if you want to write the tag for the class, and this is the way of representing the class. And if you want to represent text, char text or char, if you want to represent characters, either it may be in lowercase or uppercase characters to represent the students, or it is in directly epsilon. Or if you want to represent a student, for student you need to use an Gulment like this. Stud is nothing but a student. In between, you need to write any text and close that stud. Right here, the left hand side of each production denotes one non-terminal, like an role, a class, etc. And those symbols on the right hand side for which no productions, that is the substitutions we are doing, are defined are terminals. For example, the lowercase letters and the gulments. Gulments means these two we can call them as in gulments, or the capital letters roll. All this comes under the terminals, right? And here coming to the concept of the parse tree and how to represent the parse tree. First, initially you need to know what is an parse tree and what the constraint or conditions that we need to follow whenever we are representing the parse trees. And here each context free grammar can be represented using an parse tree. Every context free grammar I need to represent by using an parse tree. And here we're having the internal nodes and the external nodes, and each internal node is labeled by an variable in v. That means all the non-terminals are should be labeled with an internal nodes, and each leaves is an terminal symbols. That means whatever the leaves that we are generating, those are comes under the terminal symbols. And for a production like this, a tends to x1 x2 so on xk. In this, any internal node can be labeled a, and it has k childrens, and k childrens which are labeled from x1 to xk, from left to right. So always we need to take from left to right, not from right to left. We need to take from left to right. And this is the way of showing the subsequent productions just by representing with an parse tree. And this is in parse tree for production and all other subsequent productions like this. First, a tends to x1 xi so on xk, right? So a is an root node. A is an starting symbol of the grammar, so a becomes a root node. And these all after tends to the right hand side productions becomes an children nodes of this a, right? And then these can be generate and subsequent productions, whether it may be an terminal, those we can call it as an leaves, right? Here one thing we need to remember is, whenever we're representing an parse tree, the internal nodes should be an variables and the leaves should be an terminals. This is the most important thing. And from the production, a tends to this like this. A becomes an a root node, and a is having the children nodes, and those becomes an internal nodes, right? And whatever the x1 is generating and whatever the x2 is generating, those becomes an leaf nodes. That means we are generating an terminals, and this can be done from left to right. And sentinel form, and here we're having a sentential form. And what the sentential form and partial derivation tree means, here first of all you need to know what the definition of an derivation tree, and we can also call it as in partial derivation tree. And here, how to define the partial derivation tree means, a tree is a subtree of a derivation tree. That means we are deriving a tree, right? And in that, any tree that we can call it as a subtree, and either all of its childrens or in the subtree, or none of them are in the subtree, then we can call them as a partial derivation tree, right? See, here we're having an example for this. If in any context free grammar the productions are, and here I'm having three productions, and for s, a and b, and s is having one rule, a is having two rules, and b is having two rules. And here what the partial derivation tree can be means, see here, the partial derivation can be, first I need to start with a starting symbol of my given grammar with s. S is yielding with two children's A and B, and then I need to show what the A is yielding, and then after I need to show what the B is going to be yield. Right? What it means is, if a partial derivation tree contains the root S, then it is called as a sentential form. It is called as an sentential form, and the above subtree is also in an sentential form. This we can call it as a partial derivation tree. And these are the basic definitions that I am explaining you. And here there are two different approaches for drawing the derivation tree, and one is a top down approach and another one is a bottom up approach. Top down approach, in the name itself it is there, top down. What top down means, it starts with the starting symbol s and it goes down to tree and tree leaves using the productions. That means starting with s and generating the input is a top down approach. And what the bottom up approach means, initially you need to start with the leaves. That means you need to take an input as in terminals, and then you need to proceed upwards to the root, which is the starting symbol s. So these are the two approaches that we are going to learn in the concept of derivation tree. And if you know how to derive, and then you need to know what the types of derivations are. And here we are having two approaches. In those two approaches, we are only talking about in which approach we need to derive, whether it is in top down approach or whether it is in bottom up approach, and what the top down approach is and what the bottom up approach is. Coming to the top down approach, from where we need to start and from where you need to end. And coming to the bottom up approach, from where you need to start and from where you need to end. So these are the two different approaches we are having for the derivation trees. Top down, from top to bottom, and bottom up, from bottom to up. That's the, in the name itself it is there. And the most important derivations that under the derivation trees are leftmost derivation and rightmost derivation. These are the two most important derivation trees we are having here. And knowing about the definitions of what the leftmost derivation and what the rightmost derivation is, see here, leftmost derivation means it is always obtained by applying the production to leftmost variable in each step. That means after tends to, which is the leftmost variable, in that leftmost variable you need to substitute the terminals. Then it can be called as a leftmost derivation. That means starting from left you need to end to right. Same as here in the rightmost derivation. And the derivation that is obtained by applying the productions to the rightmost variable in each step. That means after tends to whatever the production that we're having, in that production you need to choose the rightmost variable and you need to substitute the terminals in that rightmost variable, and you need to start from right and you need to end at left. So from leftmost, starting from left and ending to right. For rightmost, starting from right and ending to left. So these are the two most important derivations, leftmost derivation and rightmost derivation. Right. I think you all understand what the definitions of leftmost and what the definitions of rightmost. And again, I'm recalling what the things I explained from the starting of this class. Just I start with the applications of the context-free language and context-free grammars. And after that applications, I start about the derivation tree. I explained you what the parse tree is. And then I start with an derivation tree definition. And derivation tree definition can also be called as an partial derivation tree, or it can also be called as a sentential form. And then after, I make you to understand what the approaches that we are having in this derivation trees. Two approaches we are having here, one is a top down approach and the another one is a bottom up approach. And then coming to the most important thing, that is the types of the derivation trees. Here we are having two types of derivation trees. One is a leftmost derivation and the another one is a rightmost derivation, right? And knowing about the definition of what the leftmost and what the rightmost, just here what you are doing is, from the given grammar, just by choosing an appropriate rule to derive the input string, in that appropriate rule what you are doing is, if you want a leftmost derivation, just from starting with the left variable you are substituting the terminals in that leftmost derivation. Substituting the terminals means substituting the rules, appropriate rules in the left variables, and finally you are generating an input string, right? So as the same process for the rightmost derivation also, and choosing an rule, choosing an appropriate rule for the derivation, input derivation string, and then there you need to choose an rightmost variable, and in the rightmost variable you need to substitute the rules to get an, or to generate an input string, right? This is the most important definitions what the types of derivations are. We are having two types of derivations. One is an leftmost derivation and the other one is an rightmost derivation. And what's the definition of leftmost derivation means, in this way you can define the leftmost derivation. And what the definition of rightmost derivation means, in this way you can define the rightmost definition, right? And then coming to the styles, derivation styles for the both right, leftmost and rightmost. And now I'm only showing you the derivation styles, not and tree structures, right? Derivation styles means taking the rule, taking the starting rule, and then you need to do the substitutes there, and finally you need to generate an input string in the form of the terminals. That means you need to generate the leaves, right? So only I'm showing you the derivations, not and tree structures. Here I'm showing you how to derive the leftmost and rightmost derivations. And here I'm having a question that derive the string a star of ab plus 10 from the given grammar. So this is the given grammar G. This is the input context free grammar G. This is my question, and in the question what I need to do is I need to derive the string a star of ab plus 10, right? So to get this I need to yield the input from the starting symbol of my given grammar E. So that's why I put like this. E yields the grammar A into AB plus 10. So now let's see how the derivation takes place. This is an leftmost derivation I'm showing you now. Right. This is a leftmost derivation. Initially, I start with an E tends to, because I need to scan my input from left to right. I need to start from left. I need to end to right. So initially, I need to check it out which terminal is it is A. Then after I'm having an operator star. So based on this operator, I need to choose the rule from the given grammar. So this is an appropriate rule I can choose here, because A into something is there. I am partitioning this into two parts. This is part 1 and this is part 2. In between I am having an operator star. So for that I am choosing this rule, E tends to E star E. So E tends to E star E, and where I need to substitute means I need to substitute from left variable. On the leftmost variables I need to start the substitution. See the red marks, then you can easily understand the red representation variables are the leftmost variables in the production. So in this E star E, this is the left one, this is the right one. So now I am going to derive the leftmost derivation, so I need to choose this E. In this place of E, I need to get an A, right? I need to get an terminal A. So which rule I need to choose? Which rule I need to choose here means I need to choose F. In the place of E, if I substitute F, then I can get an A, because F is having the A. So now I am choosing this F. So in the place of this A, I substitute F. So again in the place of F, if I substitute AF means F is having the rule AF. So I am choosing this AF rule and I am substituting here. So I get A star, right? So in the I do for the in this F, if I put an epsilon means it is null. So after A I am having star. So that's why I am putting epsilon in the place of this F. So I don't want anything in the place of this F, just I make it as a null, because from the input string I am having A star. So with A and star I completed this part 1. So A star is completed. Now coming to the E. And here what the part 2 is, open parenthesis AB plus 10 closed parenthesis. So I need an parenthesis, right? So to get an parenthesis, I need to choose and rule like open E and closed in this variable. And now this becomes an left, because no more variables are there in here, and now this becomes an left variable. So in this left variable, I am choosing this E tends to open parenthesis E and closed parenthesis, and just I substitute this at the place of E. Now in the place of this E, what I need, AB plus 10F. AB plus 10F. This AB plus 10F, again I am dividing this into two parts, this part 1 and part 2. In between I am having an operator plus. So for that, to get an operator plus, I am choosing the rule E tends to E plus E rule. So I am substituting this rule in the place of this E, right? So now I need to get an AB. So to get an AB, and here in the place of E I need to substitute that. So I am choosing F. In the place of E, I am choosing the rule F. So I am substituting this F in the place of E. Again, in the place of this E, I need to get an A first and then B, right? So in the place of this F, I am choosing AF. Again, I am not putting an epsilon here because I need another terminal B. So in the place of this F, I am choosing BF. BF. Now it is completed. Part 1 is completed. So I get AB. So I'm putting an epsilon in the place of this F, and then finally I get ABF, AB plus, and then I need to go for the remaining input. So up to this, A star open parenthesis AB plus was completed. Now 10 closed parenthesis is remain. So in the place of E, if I put F is having 0 F and 1F. So if I put F means at one time I can substitute 1F, in the another time I can substitute 0F, and then I make the F as an epsilon, finally I will get an 10, right? So then do this. In the place of this E, put F. In the place of this F, substitute 1F. In the place of this F, substitute 0F. Now in the place of this F, if you substitute epsilon, then finally you can get the input string A star open parenthesis AB plus 10 closed parenthesis, right? So this is the leftmost derivation. Same thing by doing an rightmost derivation. For the same grammar, for the same input string, we are deriving leftmost and rightmost derivation. Up to now, I show you how to derive the leftmost derivation by substituting the uh, variables, by substituting the rules at the leftmost variables. Now we are substituting the rules at the rightmost variables. See the difference, then you can easily get it. See, initially here also I take the rule E tends to E star E because I need to get an star in between of these two, right? So at leftmost derivation, I substitute in this leftmost variable, and in the rightmost derivation, I'm substituting in this right variable. In this right variable, I'm starting from right to left. But in leftmost derivation, I started from left to right. I think it is clear to you all. So in this place of V, first of all, I need to do this. I need to get this. I am substituting E plus C in the place of E and substituting place in the place of F. I am substituting 1F in the place of F. I am substituting 0F and put an epsilon in this place, and then E in the place of E I substitute F. In the place of F I substitute AF. In the place of F I substitute BF and then put epsilon, and here we get AB plus 10 open parenthesis closed, and here we left it out of E, and in the place of this E I put an F, and in the place of this E I put an AF, and I make F as an epsilon, and finally I get an input string. Just get the difference between how to substitute the leftmost derivation and the rightmost derivation, and finally how to generate the input strings by implementing these two derivations, right? I think you all understand. I think you all understand how to do the leftmost and rightmost derivations. Okay then. And please make a note of this example. I'm giving 5 minutes of time. Please make a note of this example. Put a heading leftmost and rightmost derivation and write down the grammar G, and write down the question, derive the string A star of AB plus 10 from G. Then put a heading leftmost derivation and make a note of these things. Always substitute leftmost variables, and put a heading rightmost derivation, and there you make a note, always substitute at rightmost variables. Then please show the derivation like this. Make a note of this example. I'm giving you time. Make a note of this example. After noting down, please, any one of you message in the chat box completed. Then I will start the next concept. Okay, then let's see the next concept. And I think you all understand how to derive the leftmost and rightmost derivations, right? And this is a derivation tree. And here we're having a question that let G be the grammar, and what the rules in the grammar is S tends to 0b or 1a, A tends to 0 or 0s or 1a, B tends to 1 or 1s or 0bb. And for the string 00110101, and first what the question is, you need to find the leftmost derivation and then you need to find the rightmost derivation, then you need to show the derivation tree, right? Derivation tree for this string. And coming to the point A, what the question A is leftmost derivation. So you need to start with leftmost derivation. And what the question is, S tends to 0b or 1a, A tends to 0 or 0s or 1a, B tends to 1 or 1s or 0bb. And from the string, what the leftmost word is 0, right? 0, two zeros I'm having, two ones, 0 1 0 1. So I choose the S tends to 0b rule here. I choose a rule S tends to 0b. And in the place of this 0b, in the place left, which is then left variable here, only I'm having an one variable. So I choose that it is in left. So in the place of this b, I'm substituting 0bb because I need to get two zeros, right? 0bb. And with this these two completed, and what the remaining string is 1 1, I need to get an 1 1. So in the place of this b, because in these two b's what the left b is this one, so in this place of b I am substituting 1b. I am substituting 1b, right? So I'm substituting 1s, not 1b, I'm substituting 1s. And now how it becomes, in the place of this, in the place of this b I'm substituting 1s, and then what, 001 is completed. In the place of this s here I'm having something. Let's see here. 00 in the place of the b, if you substitute 1s, if you substitute 1s means, because b is having the rules either 1 or 1s or 0bb, to get an 1 I need to substitute 1s from the b, right? So I am substituting 1s here in the place of this b, and now it is 001s b, right? And 1 here I get 1, and I need to get another 1. So I need to choose which rule is appropriate from the s, because I'm having s here. So I'm choosing 1a. I'm choosing 1a. So after choosing this 1a, what the string up to now I get here is 0011a b. And now a is the left variable, right? And two zeros, two ones I get here. And I need to get 01 and 01. And I need to substitute in the place of a. I need to substitute in the place of a. So I am choosing 0s in the place of a. 0s. I get 0 here, right? And again in the place of s, if I substitute 1a, I get an 1. Again in the place of a, if I substitute 0, yes. If I substitute 0, yes. Right? I get an 0. Is it clear? And in the place of this s, if I substitute a means, in the place of this s, if I substitute 1a means I get an 1. So in that way you need to choose the left variables and you need to substitute an appropriate rules from the given grammar to derive the leftmost derivation, as well as same like an rightmost derivation. That means from right to left you need to derive, from right to left you need to derive the string, and in the leftmost I start from left, then I end to right. But while coming to the rightmost derivation I need to start from right and then I need to end to left, right? And this thing I already explained in previous slide. Please make a note of this example and you yourself please try to get the leftmost derivation and rightmost derivation for this string, and it makes you practice, and also it gets very easy for you for better understanding. And the next thing, the C thing is the derivation tree. Now I need to show the derivation for this string, for this input string. And here I start with an s. I start with an s, right? And which input string is you can show for the both left and the rightmost derivations. For the both leftmost and rightmost derivations, you can show the derivation tree, but initially I'm showing it for the uh, leftmost derivation here. And s tends to 0 b. In the place of this b, I substitute 0 b. In the place of this b, I substitute 0 b b. Right. So I think you all understanding the tree structure. These are the variables s b b s b s b, and these are the left variables, and in the left variables we substitute the rules, and finally we get the input string like this. Finally we get an input string like this. And what the input string here is 0 0 1 1 0 1 0 1 0 1 0 1. And now I need to check it out whether it is an leftmost derivation tree or rightmost derivation tree. Now I'm going to check it out this, because as from the diagram it is not getting suitable for the leftmost, so I'm checking out whether it is suitable for the rightmost or not. And in the left also we start with an 0b, as well as in the right also we start with an 0b. And in the place of this 0b, we substitute 0 bb. In the place of this b we substitute 0 bb. So in the place of this b we substitute 0 b b, 0 b b. And then after two zeros I get here, right? 0 b b. And then after I substitute 1 in the place of b, 1 in the place of b. So this is a leftmost derivation. This is a leftmost derivation tree. See here, we substitute 1, right? 1 in the place of b, because b is giving an 1. In the place of b I substitute 1, and 0 0 1 is completed. And in the place of this b again I substitute 1 s. Another b is there, in that place I substitute 1 s, this one. In one b I substitute 1, in another b I substitute 1s. I think you get it. 1s. So 1s. In this place of s I substitute 0b. 0b, because s is deriving an 0b. And in the place of this b I substitute again 1s. 1s. Right? So I think up to now you get how to derive the tree structure. 1s, in the place of this s I substitute 0b, and again in the place of this b I substitute 1. So finally I get an string, and this is a leftmost derivation. Please get it clear, this is a leftmost derivation tree, not an rightmost. This is a leftmost derivation tree. Same as it is, you need to draw it, you need to derive an rightmost derivation tree. You need to show the derivation tree for the rightmost also. I think you all understand how you show the tree structure. Whatever the thing that we derived here, just in the form of the structure, a tree level by level, you need to show it like this. Then it can be called it as a leftmost derivation tree, right? And what the leftmost versus rightmost derivations. That means here where you are giving the differences between the leftmost versus rightmost. And what the question here is, for every leftmost derivation there is a rightmost derivation, and vice versa, true or false. It's true. Will use the past is to prove this. Yes, for every derivation, for every leftmost derivation there should be a rightmost. Vice versa is applicable here. It isn't true. Does every word generated by a context-free grammar have a leftmost and rightmost? Yes. If you generate a leftmost or if you generate a rightmost, means vice versa is there. So For every context free grammar, we can generate an leftmost derivation. That means reverse direction can also, it is easy to prove. And could there be words which have more than one leftmost derivation? Yes, it's totally depending upon the given grammar, or it may be leftmost or rightmost. The words which have more than one leftmost or one rightmost, more than one leftmost or more than one rightmost, it's totally depending upon the given grammar. So see, in the three differences, in the three vice versa questions also, finally we get that if there is a leftmost, automatically we can prove that it is a rightmost, right? So in the next class, I'm going to explain about the left and right recursive grammars, and then the most important concept, that is about the ambiguity in context-free grammars. If you well and known well understand and you get an ability to derive the input strings from the context-free grammars, the types of two types of derivation trees you can get the ability to derive, and two types of derivations that you can ability to derive. If you get the abilities of deriving the leftmost and rightmost, means it is very easy for you to learn the concept like an ambiguity in context free grammars, right? And this concept I will cover in the next class. And up to this session, up to this class, what the things I covered is starting with the applications of the context free languages and context free grammars, and knowing about making you to understand what the parse tree, and just showing the simple structure of the parse tree, and then what the sentential form, and then what the partial derivation tree is, and what the two approaches that we are having in the derivations, and knowing about top down and bottom up, and then coming to the types of derivation trees, leftmost derivation and the rightmost derivation, knowing the definitions of leftmost and rightmost, and with the example I explained you how to derive the leftmost and rightmost derivation styles. And then finally the derivation tree structure for the leftmost, as well as if you well get understand how to derive the leftmost derivation tree, then it is very easy for you for deriving and rightmost derivation tree. Nothing is there. If you if you perfectly did the derivation, means you can perfectly draw the representation in the form of a derivation tree. That's it, nothing is there here. For any type of an grammar, you can derive the leftmost and rightmost derivations, as well as an derivation trees for the given input string. And then finally, with the three questions, I justify that the leftmost and rightmost derivations are vice versa, right? Is it clear, all of you? Any doubts to anyone? In the next class, I will explain the ambiguity of the context free grammars.